We now begin our lecture on chapter 3.4, which is on exponential and logarithmic equations. We are going to start with learning about how to solve exponential equations first, and then we will go on to logarithmic equations. These are what we are going to cover in this chapter. First is to solve exponential equations with like bases. That means the exponents would have the same base on either side of the equation. Then we'll go on to solving exponential equations using logarithms, and we do that when the bases are not the same, with unlike bases. Then number 3, use the definition of a logarithm to solve logarithmic equations. So after we are done with exponential equations, we are going to go into solving logarithmic equations using the definition of a logarithm. We'll talk about the one-to-one property of logarithms to solve logarithmic equations, and finally we'll go on to some application-based problems involving exponential and logarithmic equations. Now first let's go over a rule that applies to exponential equations of the same base. So it says here, if b to the power m equals b to the power n, then the exponents m and n must be equal. So as long as the bases are the same and both sides are equal to each other, then the exponents must also be equal to each other. So let me just demonstrate this with an example. If we have, let's say 2 to the power 3, or let me just change this a little bit. If we have 2 to the power x and then an equal sign in between and 2 to the power 5, all right, because these two sides are equal, then the exponents also must be equal to each other. So that means x should be equal to 5, all right, because the bases are the same. All right, we cannot do this if we have 2 to the power x equals 3 to the power 5. This rule will not apply because the bases are different. All right. However, if the bases are the same, then the exponents can be made equal to each other. Now, sometimes even if the base is apparently not equal, we can change it. We may be able to change it to give it the same base. For example, if we have 2 to the power x equals 4 to the power 3, all right, we can rewrite this 4 on this side, even though 2 and 4 are appearing as two different bases. We can change this 4 and rewrite it, making it the same base as 2. How do we do that? We have 2 to the power x, like 4 cubed, can be changed and rewritten as 2 squared, which is 4, and then the whole thing raised to 3, right? So then we get 2 to the power x equals, now exponent raised to another exponent means we multiply the exponents, correct? So this is the same as writing 2 to the power 6 using the power rule. Exponent to another exponent means we use the power rule and we multiply the exponent. So this is 2 to the power x equals 2 to the power 6. Now we have a visible, or rather now we have visibly the same base of the exponents, and we can make the exponents equal to each other. X equals 6 is the solution of this equation. So let's look at these two examples here and see how they are using the rule of equal bases, or exponents of equal bases. The first one is 5 raised to the power 3x minus 6 equals 125. So at first sight, we see that the bases are different. One side has a 5, the other side has a 125. So just think a little bit. Can we make this 125? Can we make it the same base as 5? Can we rewrite it with a base 5, right? So 5 cube, 5 raised to the power 3 is 125, and that's what they have done here. 5 raised to the power 3x minus 6 equals 125 was rewritten as 5 raised to the power 3x minus 6 equals 5 to the power 3. All right, so now that we have the same base 5 and 5, we can make the exponents equal to each other, and that's what they've done here, and solve for x. So they've moved the minus 6 over to the other side. They've moved the minus 6 over to the other side, which becomes a 3 plus 6, which is a 9. So 3x equals 9, therefore x, divide both sides by 3x equals 3. So the solution of x here is a 3. For this one, for example B, 8 raised to the power x plus 2 equals 4 raised to the power x minus 3. Now, we have 8 here and we have 4 here. We can give it a common base. We can change both 8 and 4 to a common base of 2. We cannot change 8 to a base of 4 using exponents, but we can change it to a common base of 4. Common base of 2. So 8 can be written as 2 to the power 3 and 4 can be written as 2 to the power 2, and then we'll get a common base. So that's what they've done here. They've changed the 8 to 2 cube and then put the x plus 2, and they've changed the 4 to 2 squared and given it the power of x minus 3 raised to the power x minus 3. So we have 2 to the power 3 times x plus 2. We again have to multiply the exponents because it's exponent raised to another exponent. So the power rule applies here on both sides. And once we got the same base 2 on either side, we can make the exponents equal to each other, which they have done in this step here, in this step. And then the rest is just solving for x in this equation, and we get x equals negative 12, and that's the solution of the exponent. So here for these kind of problems, the main step is to change them to change the unlike bases if we can. Sometimes we cannot, but we can. If we can, then change the base of the exponent to the same value, and then you can make the exponents equal to each other and solve for x. Now we'll talk about how to use logarithms to solve exponential equations. When do we have to do that? When we cannot easily transform the bases of the exponents to the same value, then we will have to resort to logarithms to solve the equation. So let's go through the steps first, and then we'll go through an example which will make it easier for us to follow. But let's go through the steps anyway. So number 1, isolate the exponential expression. So we should have the exponential expression by itself on one side, and if there are any other terms to the exponential expression, those have to go to the other side. Number 2, take the common logarithm on both sides of the equation for base 10. So if the exponent has base 10, then we will have to take the common logarithm, because common logarithm also uses base 10. If the exponent does not have base 10, then we will need to take the natural logarithm, which is ln. Simplify using one of the following properties, and these, as you can tell, is the power rule. Ln b to the power x equals x times ln b, or ln e to the power x equals x, right? Because ln e is 1, or log of 10 to the power x equals x, and then we solve for the variable. All right, I understand that it was not too easy to follow what's going on here, so let's go on to an example and see how we can make this work. So let's look at this example of solving the equation. Look at the problem here. 5 to the power x equals 134. Now there's no way we can get 134 to base 5. We cannot write 134 as base 5, and that's why we have to use logarithms in order to solve this exponential equation. All right. So the first step said we have to isolate the exponent. All right, so this exponent is already isolated. On the left hand side, we just have 5 to the power x and no other terms associated on the left hand side, so we are good. All right, this is already in the isolated form. So we start with 5 to the power x equals 134. And then, since we cannot rewrite 134 with the same base 5, we have to take the ln of both sides. All right. Why ln and not log? Because they told us previously that we will use log if the base is a 10. If the base is a 10, we will use log. Right? Because log has base 10. If it is anything else other than 10, use ln. Use ln for any other base. Any other base. All right. So that's why they've taken the ln of both the sides. And then they rewrite ln 5 to the power x using the power rule, which is x times ln of 5. So they have expanded ln 5 to the power x using the power rule and rewritten this as x times ln of 5. On the other side, we still have ln of 134. Now we can just solve for x by dividing both sides by ln 5. So what happens? We divide this side by ln 5 and the ln 5 goes away, and this side is just ln 5, right? And we end up with x equals ln 134 divided by ln 5. Now we have to use a calculator to compute this. When we do that, we get a value of approximately rounded to 3.04 for the value of x. So the solution set is ln 134 divided by ln 5, which when computed through a calculator will give us a value of 3.04. Now this example is about solving exponential equations with base 10. The question here is 10 to the power x equals 8,000. Now there's no way we can write 8,000 in exponential form with base 10 to match the 10 of the exponent on the other side, correct? So that's why we have to resort to logarithms to solve this equation. Now, which logarithm should we use? If you remember, they said that when the base of the exponent is a 10, we must use log. Take the log of both sides, all right? Because log is the same as log base 10, all right? So here they have given us the solution 10 to the power x equals 8,000. In the next step, they have taken the log of both sides. Again, this is an equation. Whatever you do on one side, you have to do exactly the same thing on the other side. So log of 10 to the power x equals log of 8,000. And then in the next step, they have x equals log of 8,000. Now, how did they get this x from log of 10 to the power x? This is what they did. First, they used the power rule to expand log of 10 to the power x. And when you expand this using the power rule, you get x times log of 10. So we have x times this x gets multiplied with log 10, right? So we have x of log 10 equals log of 8,000, all right? And log of 10 resolves to a 1. Remember, log means here x times log base 10 of 10. So recall by the properties that we learned of common logarithms, when the base of the logarithm is same is 10 and the value next to it is also a 10, then this log base 10 of 10 um, resolves to a 1. So it's x times 1 equals, this is 8,000, log of 8,000, which is x equals log of 8,000. And then we have to just pull out our calculators and calculate what log of 8,000 is. And it is approximately 3.90. So that is the solution of this equation, all right, using the logarithmic method to solve exponential equation. Let's look at this example here on solving exponential equations. The problem given to us is 3 to the power 2x minus 1 equals 7 to the power x plus 1. So we have to solve for x in this exponential equation. Now, we have two different bases, as we can see on either side of the equation. One is a 3, the other one is a 7, and there's no way we can get 3 and 7 rewritten with the same base, right? So we have to take the help of logarithms in order to solve this equation. Now, since the bases are not 10, we have to use natural logarithms to work through it. All right. So what they've done here in the solution is they've taken ln of both sides. So we have ln, natural logarithms, that means base is e. The base of the logarithm is e. So that's why we have ln. 3 to the power 2x minus 1 equals ln of 7 to the power x plus 1. Now I always prefer to put brackets around expressions with multiple terms, indicating that it is one unit. We cannot just break it up. All right, it will always move together. So what they've done in the next step here is apply the power rule to expand the form. All right, so they have multiplied ln 3 and ln 7 with the exponent, getting 2x minus 1 times ln 3 equals, on this side too, they have multiplied ln 7 by x plus 1 by writing it on its left hand side. Okay, so that step is completed. Next is to rewrite 2x minus 1 times ln 3 using the distribution method. All right, so let me just work it on the side a little bit. You see, 2x minus 1 times ln 3 is the same as writing ln 3 multiplied by 2x minus 1. All right, so this may help you better to understand that there is distribution involved. So what they've done is they have multiplied ln 3 times 2x and then ln 3 times minus 1. And that's why we have here 2x times ln 3 minus ln of 3 equals on the other side, same thing, distribute and multiply. So x times ln 7, x times ln 7 plus ln 7 times 1, which is ln 7. All right, now keep in mind, let me just point out another thing here. When we multiply, just a second, I'm trying to get my pen up. When we have x times ln 7, you cannot write ln 7x. All right, that is wrong. This is wrong. You have to write it as x times ln 7. Why? Because ln 7 is 1 unit. All right, so x multiplied by ln 7 has to be written as x times ln 7. Please don't put the x next to the 7. All right, that'll be a mistake. So that being said, what's the next step? We have distributed here, and then for the left hand side, they have factored out the common x in both the terms. So x has been factored out, and within brackets we have 2 times ln 3 minus ln of 7. There's nothing to factor out from the right hand side, so that remains as ln 3 plus 7. All right, and now finally we solve for x by dividing both sides by 2 times ln 3 minus ln 7, right? 2 times ln 3 minus ln 7, and that's what they have here. And when we do the computation on our calculator, we will come up with an x value which is approximately 12.11. Now, in the test and assignments, you can just leave it in this form. You don't have to do this calculations, but we definitely want to see the step showing the solution in logarithmic terms, in terms of the logarithms. So ln 3 plus ln 7 divided by 2 times ln 3 minus ln 7. Now let's go through the steps of solving a logarithmic equation. Now previously we learned how to solve exponential equations, and to solve those equations we did take help of logarithms to come up with a solution. However, here the equation will be given to us in logarithmic form, and we will have to solve for x in that logarithm form. All right, so I'm going to just run through the steps first, and then we'll go into some examples which will help us to understand the process better. All right, so let me just read through the steps here. Number 1 says express the equation in the form log base b of m equal to c. Now sometimes the equations will be given to us in this form. In that case, we don't have to perform step 1. We can go straight on to step 2. However, many times it will not be given to us in that form, and then we will have to convert it, rewrite it in this form before we can begin solving the equation. Number 2 says use the definition of a logarithm to rewrite the equation in exponential form. Now by this time we should have had enough practice on converting a logarithmic expression to an exponential equation, right? So hopefully that practice will come to good use now. We have to convert log base b of m equal to c and write it in exponential form by making the b of the logarithm, making the base of the logarithm the base of the exponent, make the c on the other side the exponent of b, then the equal sign followed by m, which is put on the other side, the right hand side of the exponential equation. Once we get it in exponential form, we just solve for the variable. Now in the final step, after we get the solutions for x, we have to go back to the original equation and make sure that we include only those values of x which will keep m greater than 0. All right, m that goes with log base b should not be made less or equal to 0. So if it does, then we will have to exclude those solutions. Now let's see how they have applied the steps we learned before to solve this logarithmic equation. Log base 2 of x minus 4 equal to 3. Now recall that the first step was to put the equation in this form, log base b of m equal to c form. All right. So here we see that we already have it in this form. Over here we have log and the base is a 2 and m is this entire expression. X minus 4 is this entire expression, and then 3 is what our c is. All right, so we are good with to get started with this and solve it. So let's go through the steps here. So log base 2 of x minus 4 equals 3 needs to be put in exponential form with 2 as the base of the exponent, which is here, and then 3, which is c, goes as the exponent of 2. Then the equal sign and this entire value for m, which is x minus 4, goes on the right hand side of the equation. All right, so now we have 2 cubed, 2 to the power 3 equals x minus 4. And we can just go ahead and solve it because this seems to be converted now to a simple equation. So 2 cubed, 2 times 2 times 2 is 8 equals x minus 4. Solve for x by moving minus 4 over to the other side. Add plus 4 to 8 and we get x equals 12. So we did come up with a solution for x, but we are not done yet because we have to go back to the original equation and make sure that this is that this can be used as a solution, that m does not become a negative or value or 0 if we apply x into this equation. So what do we get here? We go into the original equation and substitute 12 into x and resolve it. So we have log base 2 of 12 minus 4 is 8 equals 3. 8 is indeed a value greater than 0. 8 here is the m. I hope you realize that. We have to make sure that m does not turn into a negative value or a 0 when we substitute 12 into x. It doesn't. 8 is a positive value. So yes, we can use it as a solution for x. So yes, it's true. The solution set is 12. Let's go through the second example now, which says solve 4 times ln of 3x equals 8. Now, the first step again is to rewrite the form in log base b of m equal to c, correct? So let's see if this is in this form or not. We have 4 times ln 3 times x equals 8. So this is not quite in the log base b of m form. We have to remove 4 and isolate the logarithmic expression on the left hand side. So let's do that. In order to get rid of the 4 from this side, we have to divide both sides by 4, correct? So we have 4 times ln of 3x divided by 4 equals 8 divided by 4. Let's cancel out the 4 on the left hand side. On the right hand side we have a 2, and that's what they've started with in the solution. They have ln of 3x equals 2. It is now in this form. Log, it starts with the log, correct? Ln 3 of x. Earlier there was a 4 before the ln. All right, so now we can go and rewrite this in exponential form. So ln means log base e, correct? So let me write that down. Ln of 3x is the same as saying log base e of 3x equals 2. So how do we rewrite that? With in exponential form, we have the e as the base of the exponent. This 2 goes as the exponent of e, then equal sign, and the 3x goes on the other side of the equation, correct? And now we can solve for x by dividing both sides by 3, and we have x equals e squared divided by 3. So the final step is now to check if when we plug in e squared divided by 3 into x in the original equation, then we should come up with a positive value. So 4 times ln of 3 times, they substituted e squared divided by 3 into x. Is it equal to 8 or not? So 4 times ln e squared equals 8. Now, ln e squared is whatever this exponent is for the e, right? That's a property we had learned before when we have, let's say, let me write it like this, log base e of e squared. When we have the base of the logarithm and the m here, the same value, in this case e in both, then the solution, the result, not the solution quite, the result is whatever this exponent is. This is equal to 2. So ln of e squared calculates to 2. So we have 4 times 2 equals 8. Both sides are equal. So our solution is e squared divided by 3. Now we'll work on a slightly different equation, which is log of x plus log of x minus 3 equals 1. Now the first thing we note here is that the logs do not have a visible base to it, which means that the base is a 10, right? Another thing to note is that we have two terms on the left-hand side. Both have logs in them, and they are both of the same base, log base 10, right? And there is a plus sign in between. So when that situation happens, then we can condense this entire expression on the left-hand side and rewrite it with a single log using the product rule of logarithms that we learned before. All right, so let me just rewrite here what the product rule states. It says log of x times y can be written as log of x plus log of y. All right, and vice versa. So if we have log of x times y, we can either expand it and write it as log of x plus y, or if we have it in an expanded form, we can condense it and write it in as log of x times y. And that's exactly what we are going to do here. And in the solutions, they have, in the second step, that's exactly what they have done. All right, they have taken the log, written it once, and they have multiplied the m values that go with each log, which is x times x minus 3. And on the other side, we have equals 1, right? So now we have to change this logarithmic expression on the left-hand side in exponent form. Again, the base of log is 10, so we have the base of the exponent as 10. Then we took the 1 from the right-hand side and made it the exponent of 10, and we moved the x times x minus 3 and wrote it on the other side of the equal sign. So now we have an algebraic expression without the log in exponent form. So 10 to the power 1 is 10. We have to multiply x times x minus 3 and rewrite it as x squared minus 3x. So we are getting closer to to a quadratic equation now, we move the 10 over to the other side and it becomes a minus 10. So one side is zeroed out. Now we see if we can use the factoring method to solve this quadratic equation and find the solutions of x. And this trinomial is factorable. The factors of negative 10 that would add up to a negative 3 are negative 5 and 2. So we have it in factored form here as x minus 5 and x plus 2. And then we make each factor equal to 0 and solve for x. All right. However, we are not done yet because we have to take these solutions of x and plug it into the original equation and make sure that none of these m values become a negative value. All right. Now we are going to do that in the next slide. They have shown that work. So this was just part 1. All right. Until we do that test, we will not be able to write our final solution for x. This is the last step for solving the equation log x plus log of x minus 3 equal to 1, which we were working through in the previous slide. We had found two solutions for x. One was a 5 and one was a negative 2. And now we have to go in and plug in each of these two values into the original equation and see what or whether it solves the equation, whether it's valid for the equation. So we have log of 5 plus log of 5 minus 3 when we plug in the 5, and we get log of 5 plus log of 2 is it equal to 1, and when we do the computation we have log of 10 equal to 1. You see what they have done here? They have applied the product rule on log of 5 plus log of 2 and rewritten it as log of 5 times 2, which is log of 10, which equals 1. All right. However, when we plug in negative 2, first of all, this m, the value next to the log, can never be negative or can never be a 0. That itself will annul the solution. All right, so here we see log of negative 2 plus log of negative 2 minus 3, it's negative 5, so this immediately becomes invalid. So negative 2 will not be a solution of the equation. There'll be only one solution for this particular equation, and that is going to be 5x equals 5, right? Now we learn solving logarithmic equations using what's called the one-to-one property. The one-to-one property essentially says that if you have on either side of the equation two logs, all right, two logs with the same base, let's call that base b, then whatever, as long as we have logs to the same base and an equal sign in between, then m, we can make this m equal to the n. All right, so in the next step, what we can do is we can just rewrite m equals n, and if m and n are expressions with x in it, then we can solve for x. That's essentially in a nutshell, what the one-to-one property is about. So let's just read through the steps here. It says step 1, express the equation in the form log base b of m equals log base b of n. And it must be written with the coefficient of 1. All right, this form involves a single logarithm whose coefficient is 1 on each side of the equation. So we cannot have a 4 of log base 10 of something. All right, that 4 should not exist. The coefficient should be a 1 of the log. Number 2, use the one-to-one property to rewrite the equation without logarithms. If log base b of m equals log base b of n, then m is equal to n is just what I told you here. all right, at the start. Number 3, solve for the variable, and number 4 is always check for the solutions. Plug it into the original equation and make sure that both m and n are greater than 0, right? So let's go through an example of that. Let's go through the steps now of solving a logarithmic equation using the one-to-one property. The equation given to us is ln of x minus 3 equals ln 7x minus 23 minus ln of x plus 1. Now the first thing that we note is all the logarithms here are ln, so they all have the same base. So that means we can later on go ahead and apply the one-to-one property. But before that, look at the right-hand side. The right-hand side has ln of 7x minus 23 minus ln of x plus 1. So since both these terms have ln in it and a minus sign in between, what we can do is we can apply the quotient property to collapse this with a single ln. So recall what the quotient property is. It said ln, or any logarithm with any base for that matter, ln of x divided by y can be expanded to the form ln of x minus ln of y and vice versa, right? So we can either expand, if it's in the form x divided by y, we can uh, expand it and write it with a minus in between the two terms. Or if it is already in the expanded form, we can write it in a compressed form, contracted form of ln of x divided by y. All right. And that's what we are going to do here to collapse ln 7x minus 23 minus ln of x plus 1 and write it as a quotient. So now we got ln of x minus 3 on the left hand side equals ln of 7x minus 23 divided by x plus 1. All right. So now that we have a single term on the left hand side and we have collapsed the right hand side to a single term, all we need to do is equate the m and the n. Just we can remove the ln and make x minus 3 equal 7x minus 23 divided by x plus 1. Okay, and then it is the same process as solving a rational equation, right? So let's see what we are doing here to solve it. We first have to get rid of the x plus 1. Now I always prefer, whenever there is an expression with multiple terms, I would like to surround it with brackets, because that reminds me that the whole expression has to be treated as a unit. All right, we cannot break it up. Right now, so to go back to solving the equation, we have to get rid of the denominator first, which is x plus 1. So we multiply both sides by x plus 1 in order to get rid of the x plus 1 on the right hand side. I have to do the same thing to the left hand side as well. So what happens is x plus 1 and x plus 1 on the right hand side divide, and we are left with x plus 1 times x minus 3 on the left hand side, and on the right hand side we just have 7x minus 23. So right, so this and this also divides. So this is what we are left with, x minus 3 times x plus 1 equals 7x minus 23. Now we have to multiply these two binomials, all right, and rewrite it here as x squared minus 2x minus 3 equals 7x minus 23, right? And then we move all our terms to the left hand side and make one side equal to 0, because this is a quadratic equation. to solve a quadratic equation, we have to make one side equal to 0. And then we can either use the factoring method, or if we cannot factor it, we will be using the formula, the quadratic formula. But in either case, we have to make one side equal to 0. So x squared minus 9x plus 20 is factorable as x minus 5 times x minus 4. Then we make each side equal to 0 and solve for x. So we get x equals 5 and x equals 4. Now this is going to continue because remember, we have to plug in these values into the original equation and make sure that x minus 3 or 7x minus 23 or x plus 1 do not become a negative value or a 0. So we continue this in the next slide. So we have found the two solutions of x for this equation, and now we have to take each solution, plug it into the original equation, and see whether both sides equal each other when we plug that value in. So we start with 5, x equals 5, and we plug it in to wherever there is an x in the original equation, right? So we get ln 5 minus 3, which is ln of 2, equals ln 7 times 5, plug in 5 into this x, minus 23, and then minus ln of 5 plus 1. So ln 7 times 5, 35, minus 23 is ln 12, and then minus ln 5 plus 1 is a 6. And then we can use the quotient property to write this ln 12 minus ln 6 in contracted form of ln 12 divided by 6, which is ln 2. So ln 2 is equal to the ln 2 on the left hand side. Therefore, the two sides are equal to each other. We come to the conclusion that 5 is indeed a solution for this particular equation. Now we have to do the same thing with x equals 4. So let's proceed to the next slide and see how 4 works on this equation. So this time we plug in 4 wherever there is an x in the equation. So we write it as ln 4 minus 3, which is ln 1, equals ln 7 times 4, which is 28, minus 23, which is ln of 5, minus ln of 4 plus 1, which is also ln 5. Again, we use the quotient rule to write this in a contracted form. So ln of 5 divided by 5 is ln 1. So ln 1 is equal to ln 1. Both sides equal each other. Therefore, the equation is true for both x equals 5 and x equals 4. So both 4 and 5 are the solutions of this equation. Now we are going to end this section of the chapter with a couple of application problems on exponential and logarithmic equations. Right? Now this particular problem is on compound interest. So what I'm going to do is I'll just read what the question is saying, and then we will kind of dissect it further and go into solving it. Right? So it says, how long to the nearest tenth of a year will it take $1,000 to grow to $3,600 at 8% annual interest compounded quarterly? All right. So I go into the bank with $1,000 and invest it or deposit it at a certain interest rate, annual interest rate. And then based on how many times the interest rate is calculated and put into my account, it will end with a certain value at the end of the tenure. All right. So that's what the problem is about. The question is asking, how long will it take for $1,000 to grow to $3,600 at an 8% interest rate compounded quarterly? All right. Now this word quarterly is very important. Let me just explain what this means. The word quarterly means how many times the bank is going to calculate the interest and deposit it into our account. How many times a year? All right. So quarterly, quarter means 4 times a year, right? So means 4 times, let me write that down, 4 times a year. They are going to calculate the interest and put that interest, add that interest to my balance. Okay, so let's go through the equation given to us to calculate compound interest. It's A equals P, and then we have brackets. Within brackets, we have 1 plus R divided by N, and the bracket is raised to the power N times T, which is the exponent of this formula. All right, so let's identify what A, P, R, N, and T are. P is the principal amount. It's the amount that you start your account with. It's the amount that you deposit to the bank the first time you go there. That's $1,000. So in this example, $1,000 is our P, or principal amount. Okay, it's going to be our P. P equals 1,000. So let me write this here. Principal, and in our case that's 1,000, right? A is the end amount that you will get after the account matures. All right, so A represents the end amount, what it will grow to at the end of the tenure. All right, so in this case it'll grow to 3,600. So A is, all right, this 3,600 is the is what we are going to plug into A. And so let me just write, it's the end amount, so to speak. All right, then within brackets we have a R, which is the interest rate. All right, so the interest rate is 8%. We have to convert that to a decimal when we plug it into this equation. But for now, just understand R represents the interest rate. N is the number of times the interest is getting calculated, is getting compounded. So N is going to be equal to 4. All right, so our N is going to be 4. And they say compounded quarterly. They don't write explicitly 4 times in this question, but it is up to us to understand that from the wording and figure out that's what N is going to be. Quarterly means 4 times a year. So we know what N is. It's the same thing in the exponent. T represents the number of years that you leave the amount in the bank before it matures. So T is the time, and that's what we have to find. It says how long, so that represents the time. Okay, so now that we have identified the different variables in this equation, let's go and plug in the values we already know. So A is 3,600, so we plugged in 3,600 into A, equals, then P is this 1,000, so we wrote 1,000 here, then within brackets 1 plus R is derived from this 8%. You have to convert that to decimal, so 0.08 divided by 4. 4 is number of times the interest gets compounded, so divided by 4. And then in the exponent we plugged in the same 4 for N, but the T is what we need to find out. So we don't have a value for T. That's what we would need to find out. So how do we proceed with that? So we got 3,600 equals 1,000 times 1 plus, what they did first was they did the division inside the brackets. 0.08 divided by 4 is 0.02, and 1 plus 0.02 is 1.02. So they added the values in the brackets. So in this step here, it's 3,600 equals 1,000 times 1.02 raised to the power 4 times T. All right. So what did we do now is we divide both sides by 1000. All right, so we have to solve for t. So the first step is we have to isolate the exponent part of this equation, right? We have to isolate the exponent part. So we have to get rid of this 1000, right? So divide both sides by 1000, right? Divide both sides by 1000 and we will end up with 3.6. That's what they have here. 3.6 equals 1.02 raised to the power 4t. So now that we have isolated the exponent part of this equation, you take the ln of both sides, right? We take the ln of both sides and we get ln 3.6 equals, now we are using the power rule to bring that 4t to the left hand side of ln. Again, the power rule of exponents. So that's why you see 4t to the left of ln. So 4t times ln of 1.02. Now we just go and now that 4t is at the same level as ln 1.02, we are solving for t. Divide both sides by 4 ln of 1.02, correct? 4 ln of 1.02, and we get this. The rest of it we have to use our calculators and solve for, and we will get a t of approximately 16.2 years. So after approximately 16.2 years, $1,000 will grow to an accumulated value of $3,600. Now let's finish this off with this last application problem on logarithmic equations. I'm going to read through it first. The percentage of adult height attained by a girl who is x years old can be modeled by f of x equals 62 plus 35 times log of x minus 4, where x represents the girl's age from 5 to 15 and f of x represents the percentage of her adult height. At what age has a girl attained 97% of her adult height? So what this equation is about is it's telling us what the percentage of a girl's adult height is going to be. So f of x is going to be a number that represents the percentage of a girl's height whose age is between 5 and 15. And what is x? X represents the girl's age from 5 to 15 years. So this equation is going to take in the age. We can plug in a value of a girl's age, but it has to be from 5 to 15. So you see the domain here is constrained between 5 and 15. And once we plug in the value for x into this equation, it will calculate the percentage height that a girl will attain at that age. All right. The question gives us a specific percentage. It says, at what age has a girl attained 97% of her adult height? So let's see how we go about solving this. It says f of x equals 62 plus 35 times log of x minus 4. That's something we just wrote from the question itself. It's given in the question, all right? So this is just using that same formula. Now, we have to plug in some values here. F of x, remember, is the percentage. So f of x is going to be this 97%. So we are going to replace f of x with 97 and then equal 62 plus 35 times log of x minus 4. So x is what we are being asked to find. At what age? Age is the x value. All right, and that's what we need to find, the x. So this is a logarithmic equation. How do we go about solving it? First, we have to isolate our logarithm. We have to have the logarithm by itself on one side and remove all the other coefficients or other terms from the right hand side to the left hand side. So we start with moving 62 first. So move 62 to the other side. 97 minus 62 is a 35. So once we do that, what are we left with? 35 equals 35. This 35, which is the coefficient of the log, so 35 times log of x minus 4. So we have to remove this 35 as well. So divide both sides by 35 to remove that, and we get 1. 35 divided by 35 is a 1. So 1 equals log of x minus 4. Now keep in mind this is log, therefore the base is a 10. All right, so it's as good as saying log base 10 of x minus 4 equals 1. All right, so if we write this in exponent form, remember in solving logarithmic equation we have to rewrite it in exponential form. We have to convert the logarithmic expression into exponent. So 10 to the power 1, x minus 4 goes to the other side. So we have 10 to the power 1 equals x minus 4. Therefore 10 equals x minus 4. Solve for x, bring the minus 4 over to the side of the 10. So 10 plus 4 becomes x equals 14. So by the age of 14, a girl is expected to attain 97% of her adult height using this formula given. All right. So that concludes exponential and logarithms or logarithmic equations. We have one more section left in this chapter, after which we will be done with chapter 3.